Hey guys, welcome to graphing systems of equations. And when we graph systems of equations, what we're actually going to be doing is we're going to be solving those systems. And so there's going to be multiple ways that we can solve systems of equations. And today we're going to focus on one method called graphing. So what is a system of equations? A system of equations is a set of two or more equations in the same variable, so two or more. We're going to be concentrating this lesson on just two equations. Okay, the same variable means that when you make up an equation, they're both in the same. Like here, it's y and x. So in this equation has y and x too. So this is an example of a system of equations. And there's two of them there, and we know it's a system because we use this curly brace, okay, to denote that system of equations. So when you solve an equation, solve a system, you're looking for a solution. And so that solution is a set of values. And that set of values are called ordered pairs. So we're looking for the set of values for the variables that make all equations true. So there's three things that can happen when we talk about linear systems in two equations. With two equations, one is that you can have intersecting lines. Okay, and when we have two or more lines that intersect, we say that's an independent system. And there's one solution, it's one unique solution. So there's one ordered pair here that satisfies all the equations of my system. Now, the second type of solution is called coinciding, which tells us that all the equations are the exact same. When we have coinciding lines, we call that a dependent system. Okay, and there's no unique solution because there are infinitely many solutions. And the final type of solution we can have are parallel lines. And we call that an inconsistent system because there is no solution to that system. Okay, the lines are parallel in that system, so there's no solution. So when we solve these systems by graphing, we're going to be looking for one of these three methods. Okay, one of these three things are going to happen. Either the lines are going to intersect, they're going to overlay, or they're going to be parallel. So that's what we're going to look at when we solve these systems. So let's go ahead and do this. Now, the first example, we're going to solve the system y equals x minus 2 and y equals negative 2x plus 7. Both these equations are in slope-intercept form. Okay, that's important to know. So I'm gonna take what the example's given me, and so I'm gonna plot these equations in slope-intercept form. Okay, and so you can see that they're plotted here. But let's go ahead and see how we got to that value. Okay, so I'll take care of those. And now let's plot y equals x minus 2. So I'm going to go ahead and my y-intercept is negative 2, so I'm going to plot that in blue. And my slope is 1, so I'm going to go up 1 over 1. Now I'm going to go ahead and connect that, and that's what you saw earlier. We're going to connect this graph, and we're going to start here. We're going to go here. There we go. So there's our first line. Now, let's look at our second line. It's y equals negative 2x plus 7. So my y-intercept here is 7, so I'm going to plot that in red. And then my slope is negative 2, so I'm going to go down 2 and to the right 1. We get that right 1. Remember, make that a fraction, 2 over 1. That's where we get our run from. So now I'm going to go ahead and connect these. Now it's very important that when you graph these, if you have a ruler, okay, because this can be very challenging in getting the exact solution. So I'm going to go ahead and that looks pretty good right about there. So now this is intersecting, so there's a unique solution. So I'm going to look to see where these two lines intersect, and it looks like they're going to intersect at 3, 1 right there. So that looks like my solution. So I'll go ahead and write that. The solution we think is 3, 1. So that's our unique solution. So 3, 1. Now let's test it. So how do you know this is a solution? So when you have y equals x minus 2, let's go ahead and substitute 3 in for x and 1 in for y. So you have 1 equals 3 minus 2. Is that a true statement? Yes, it is. So that made our first equation true. Let's look at now y equals negative 2x plus 7. So there's a little more work here. Our y value is 1. Our x value is 3. So negative 2 times 3 plus 7. Does that equal 1? Does 1 equal negative 6 plus 7? It does. So this does work out. And so that's what they mean in that first slide when we say the solution has to make all the equations of the system true. These are two true statements, so we know that's a solution. In our second example, we've changed it up just a little bit here, and we have one system that's in slope-intercept, or almost slope-intercept form, and we have one that's in standard form. So this second equation, I'm just going to go ahead and rewrite. X plus y equals 2. Well, that's just the same as y equals negative x plus 2. And so let's go ahead and plot that first in blue. So my slope is 2. So I'm going to go ahead and put 0, or not my slope, I'm sorry, my y-intercept is 2. And my slope is negative 1. So I'm going to go down 1 over 1. And let's go ahead and draw that graph in. So we'll go ahead and connect these 2 points. Okay, we can see we're a little off there. Let's see if we can move that just a bit. Pretty good. Okay, now my second equation is what we call standard form. So we can use intercepts to graph that, and that's what we're going to do. So I'm going to have 2x. So we have 2x plus 4y equals 12. Now remember, when we want the x-intercept, we set y equal to 0. Okay, when we want the y-intercept, we set x equal to 0. Okay, so those are the two things we need to think about. So when we set y equal to 0, we're left with 2x equals 12. When we set x equal to 0, we're left with 4y equals 12. So in this case, we have x equals 6. Here we have y equals 3. So when x is 6, we knew that y was 0. When x was 0, we know that y is 3. Those are our two intercepts. So let's go ahead and plot those. 6, 0 is here, and 0, 3 is here. Okay, so this is a tricky one, so we're going to try to graph this and make sure we get a straight enough line, because this is a problem when you graph. You can run into not getting your graph exactly on point. So we'll go here. Okay, so that should be good. And then I'll go ahead and extend this graph out as best I can. Okay, and let's see, we'll try to move this graph a little bit. Whoops, here we go. Doesn't want to, there we go. Okay, let's see. Does not want to move. Okay. So when we look at it, it appears that the solution is going to be right here. Okay, these lines are a little bit thicker. Our solution actually ends up being over here, negative 2, 4. And I'm going to show you why here. So it appears that the solution is there. Let's put it in red. Okay, but my graph is a little bit off. Okay, I've already done this ahead of time, so let's see if my solution is correct. I believe it's negative 2, 4. So that's a pretty easy thing to do. So we're going to have 2x plus 4y equals 12. And then we're going to have x plus y equals 2. So then do negative 2, 4, does negative 2, 4 work? So let's try it. So 2 times negative 2, that's my x value, plus 4 times 4, which is my y value, does that equal 12? So does negative 4 plus 16 equal 12? It does. Now does x, negative 2, plus 4 equal 2? It does. So that is the solution to our system. So again, I want you to be careful. And when we talk about graphing, so this is one of the things that can happen. You would have plugged in negative 1, maybe 4, and you would have gotten the wrong value. It should be negative 2, 4. But you know, writing on a tablet and trying to draw this without a ruler can be very challenging. So that's why we have other methods of solving systems of equations. All right, so in this example, solve the system x equals 10 and x equals y minus 10. So I wanted to put this in here because I know we're talking about graphing, but let's say I don't have room on my graph paper, and I have this generic graph in here. So what happens if we change these? Instead of going by ones, we go by 2. So that makes this 10 right here, and this one also 10. Okay, so x equals 10. If I was going to graph that, that is a vertical line. So I can make a vertical line going through, just going straight up 10. Okay, so there's my line. I'll keep that going. I'm going to keep this going because you'll see here in a second we're going to need more graph. Okay, so now my second equation is x equals y minus 10. Well, x equals y minus 10. So x equals y minus 10. That's the same thing as y equals x plus 10. So mathematically, if I was going to argue here, I could say, well, if I know that x is 10, couldn't I just put 10 here? And so my y value is 20. So my solution would be when x is 10, y is 20. And that will be the solution. But let's just plot this anyway. So we have y equals x plus 10. So that means my y-intercept is 10. My slope is 1, right? So it's just going to go up 1 over 1. So it's not very high, not very much, something like this. Okay? So up 1 over 1 if these are by 2. So somewhere in the middle. That's a rough estimate. And let's go ahead and plot that. So let's get our line. We'll go here. And so look how far this graph grows. I didn't have enough spots to do that. So what is this intersection point? What would this intersection point look like? So right there, that's my solution. So I plot these two lines, it's above, and I'm telling you that it's 10, 20, because if x equals 10, so 10 equals 20 minus 10, right? So there's our solution. It is 10, 20. So in our last system, solve the system here. And so we have 7x minus y equals 6 and negative 7x plus y equals negative 6. So these are both in standard form, but they're not really easy. If I wanted to find the x-intercepts, they're going to be decimals, and so I don't like that. So I'm going to just rewrite each equation. Negative 7x plus y equals negative 6. Okay, so let's solve both of these equations for y. So here I'm going to subtract 7x, and I'm going to be left with negative y equals negative 7x plus 6. Now I have to multiply through by negative 1, so I'm going to change that sign, change this sign, change this sign. So my equation is y equals 7x minus 6. So I can go ahead and plot that. My y-intercept is negative 6, so I'll go ahead and do that. And my slope is 7, so I'm going to go 1, 2, 3, 4, 5, 6, 7. Whoops. Here and over 1, which is right there. Get my connector and go ahead and plot this equation. There's my line. Okay, so now I'm going to look at the second equation of that system, and I'm going to solve for x. So I'm going to, or solve for y. I'm going to add 7x to both sides. And thankfully, there's only one step to do. So we get y equals 7x minus 6. So wait a minute, these are the same lines. So if I go ahead and plot this in blue, I'm going to get the same two ordered pairs. The y-intercept and the slope are the same. They are coinciding lines. So that means there's infinitely many solutions. So if I go ahead and plot this, and I'll do that. Okay, go a little past there so you can see. So they're the exact same lines. So that means there's infinitely many solutions. Okay, so that's graphing systems of equations, okay, and these are linear systems, and so if you guys have any questions or comments, you can type them below. Again, you can see that there's been some issues with the graphing, and so graphing is not always the best aspect, and you'll see that in the second and third video that we have other options. So again, questions or comments, go ahead and type them below, or you can go ahead and email me, and we'll see you next time.